Hello everyone. In my last two videos on wireless power transfer system, I tried to show how a simple wireless power transfer system can be built. I also show some analysis in part 2. And now in this part, I'll try to show some practical load considerations and some applications like charging a cell phone and charging a battery pack like that. In this part of the video, I would like to discuss effective coil separation or range, types of loads, voltage requirements, power requirements, and some practical examples like charging a cell phone and a 12-volt battery pack. To drive any electrical device with the wirelessly transferred power, the most important issue immediately comes is the type of load that we intend to drive. To do the load test, I need an adjustable load, starting with coil separation of 5 cm and varying the load resistance. I measure the current through the load and voltage across this load. Same test is done with coil separation of 7 cm and 10 cm. Now for the load, we need a low resistance and high power load. Instead of using a high power adjustable resistance, I used an active load, which is easy to implement and cheaper alternative. A high power transistor with a heatsink is used as a load. A high value and low power variable resistor is used in the base circuit of the transistor. As the gain of this transistor is nearly 200, a very small current in the base becomes 200 times higher at the collector circuit. The collector emitter will give much lower resistance as a result. I also tested the circuit with another transistor BD42G, which has higher gain and power. The photo shows the practical active load that I used. So 1K to 51K resistance at the base transformed to 2 ohm to 270 ohm at the collector. As the power is mostly dissipated by the transistor, it should be mounted on a heatsink like this. This plot shows the relationship between the 50K potentiometer resistance with the output resistance. So you can see that 1K to 50K becomes 2 ohm to 270 ohm. Here is the photo with the active load connected at the secondary output after the rectifier circuit. Keeping the coil separation 5 cm and the input voltage 13 volt, the active load was varied from 270 ohm to 2 ohm. The plot shows the relationship between the power and efficiency versus the output voltage. We can see that the maximum power and maximum efficiency appears at two different voltages. We may consider at around the output voltage of 16 volt, power and efficiency both are optimized. At this point, the output load resistance is around 35 ohm. Increasing the coil separation from 5 cm to 7 cm, the load resistance was varied in a similar fashion as before. This time the plot shows that the load for optimum output power and efficiency is around 12 ohm, which is less than that of 5 cm separation. Increasing the coil separation further to 10 cm and varying the load, we get this plot. Now in this case, the optimum load becomes 7 ohm and output voltage is also decreased. With the increasing separation, the output power also gradually decreases. Now, keeping the coil separation 10 centimeter and output load 6.7 ohm, which is close to 7 ohm, input voltages varied from 10 volt to 16 volt. The output voltage follows the input voltage as shown. I also tried to calculate the power output with varying load for these three different coil separation values. The results are shown here. You can see the optimum load resistance decreases as the coil separation increases. Optimum load with coil separation is plotted here. As you can see that coil separation of 5 centimeter, the load is more than 35 ohm, and then at 7 centimeter it is around 12 ohm, and at 10 centimeter around 7 ohm. The calculated data shows similar trend. With the increasing coil separation, the output power also goes down from 13 watt to 8.5 watt. In this slide, all the results are summarized. What happens when we increase the coil separation? As you can see, maximum obtainable power goes down with coil separation. Voltage will go down. However, current will go up. So for a wireless power transfer system, these three factors are very important. Coil separation, nature of loads we are interested in, voltage and current requirement. Now all these load studies are very important as our goal is to deliver power to a load. We need to power some certain load and maintain the required voltage and current. If our load is fixed, we need some circuit or DC to DC converter to maintain a fixed voltage across the load. In a complex wireless power transfer system, a feedback loop is used to ensure delivery of constant voltage and power to the load. If the load is changed or the coil separation is changed a little, the control system changes the PWM of the input converter and changes the input voltage as well in accordance with the load requirement. However, I am not going to discuss this kind of control system. I would rather utilize a simple circuit to drive some loads. Any wireless power transfer system has some losses in various parts. In the primary side, the coil resistance, the converter resistance, and the wiring resistance consume some power. On the secondary side, the coil resistance and the rectifier and converter resistance and the wiring resistance consumes some power as well. These are some of the practical loads that can be considered to be driven with a wireless power transfer circuit. 5 volt USB power driven loads and battery pack. It needs usually for slow charging 500 milliampere and 1 to 3 amp for fast charging, and 3.7 volt lithium ion battery. It needs 4.2 volt and 1 to 2 ampere is needed for charging. 12 volt driven loads and battery pack, usually 11.1 volt output, needs 12 volt for charging. 20 volt driven loads and battery pack, usually 18.5 volt at the output and needs 20 volt for charging. Power drills, a lot of power tools like drills, blowers, saw, etc. use this 12 volt battery. And 12 volt auto battery charging, 14.5 volt is needed for charging. Higher the current, the faster the charging. Whatever the types of loads we are trying to drive, all kinds of loads should be considered as resistance. For instance, case number 1, we would like to charge a standard 18650 lithium ion battery. So this kind of battery usually have internal resistance of 0.075 to 0.15 ohm. The terminal voltage when fully charged around 4 volt, and recommended charging current is 0.5 to 2 amp. So this can be considered like a 4 volt battery with a resistance around 0.1 ohm, and this we can think of a 2.1 ohm resistance. So this is the load resistance we have to think of connected at the output of the wireless power transfer circuit. So consider the charging current is 2 amp and internal resistance is 0.1 amp. So we can find that the power needed to charge is 8.4 watt, and this gives us the equivalent resistance 2.1 ohm. The second case is USB-C cable charging a 1 amp load. So 5V volt by 1 amp, that is 5 ohm. Then we can consider the load resistance to be 5 ohm. In the third case, we intend to charge a 12 volt lithium ion battery pack. Usually 12 volt lithium ion battery pack consists of 3 18650 standard lithium ion batteries. So actual terminal voltage should be 11.1 volt. It needs there is a small balancing circuit within the battery pack, so it needs 12 volt to charge. And if we consider we are charging with 1 ampere current, then this can be considered to be a 12 ohm load. So in case of auto battery, when the terminal voltage reaches 14.5 volt, the battery is considered to be fully charged. So 14.5 volt, and if we consider our charging current to be 1 amp, then a auto battery can be considered to be a 14.5 ohm resistance. Let us consider that our coil separation is maintained at 10 cm. We would like to charge a lithium ion battery. Our system can give us 9.8 watt and 8.3 volt at the output for an input voltage of 13 volt. So in this case, the input voltage and power are both higher than required. We can easily use a DC to DC converter to reduce the output voltage to 5 volt, and then the usual charging circuit for the lithium ion battery charging. For a 5 volt USB device, we need a simple DC to DC converter circuit to reduce the voltage to 5 volt. To charge a cell phone, we need 5 volt and 1 ampere or 0.5 ampere. So the equivalent load is 5 ohm or 10 ohm. If our DC to DC converter is 90% efficient, at the input we need 5.6 watt, considering 1 ampere charging current. So just if we take a look at our previous graph, the output voltage versus power, we can see that for 5.6 watt, the rectifier output voltage should be around 14 volt, and the current should be 0.4 amp at the output. So rectifier circuit will see 35 ohm connected across the terminal. This photo shows a DC to DC converter circuit is used to charge a cell phone. At the output we are getting constant 5 volt and input around 14 volt. To charge a 12 volt lithium ion battery pack with our wireless power transfer system and maintain the same input voltage to be 13 volt, the charging current will be less than 1 amp. So similar to the previous case, we can find the equivalent load, which is around 17 ohm, and the charging power would be 8.5 watt, and the rectifier circuit will see around 21 ohm. This slide shows the photo. The DC to DC converter at the output is charging a lithium-ion battery pack. For a 12 volt auto battery to be fully charged, we need 14.5 volt at the terminal voltage. A discharged battery usually has less than 12 volt terminal voltage. As the battery starts accumulating charge, the terminal voltage goes up. Now with our wireless power transfer system and using 13 volt at the input, as you can see at 10 centimeter distance, we won't get much current for charging power. So charging is still possible with a starting current of 700 milliampere and will drop to 300 milliampere when it is fully charged. So the charging process will be slow. If we have to increase the charging current, we need to increase the input voltage higher than 13 volt. Also to be noticed that the efficiency drops from the peak if we keep charging at this voltage level. To maintain the maximum efficiency for higher charging voltage, we need to increase the input voltage from 13 volt to higher voltage. So far, I have not said much about how to increase the range of wireless power transfer. In the last video, I used an equation for the ratio of the output power to the input power, which is shown here. There are some ways to increase the range. One of this is to increase the physical size of the coil. That is to increase the diameter of the coil. As the coil separation increases, the coupling factor decreases, but for larger diameter coils, the value of K goes down at a much slower rate compared to the smaller diameter. In the next video, I'll try to show how to increase the range of wireless power transfer. I connected an active load at the secondary after the rectifier circuit. I kept the coil separation 10 centimeter at this moment, and you can see voltage and current. Voltage is 15.8 volt and current is very little as the load resistance is high initially, and as I am decreasing the port, that is a 5 kilo port, you can see the current going up and voltage going down. So the transistor is mounted on a pretty large heatsink, as that will dissipate a lot of power. So instead of using a low value high power resistance, I am using active load. It is cheaper to make. This kind of experiment was done with 5 centimeter and 7 centimeter coil separation as well. After a few minutes of test, you can see that the heatsink becomes pretty hot, as the transistor will dissipate a lot of power. Now a regulator circuit and a 12 volt lithium ion battery pack is connected, and it is getting charged with this power transfer system. This regulator circuit, I used it before with some other circuits as well. Then I set the regulator at 5 volt, and I connected a mobile phone to get it charged. Now the regulator is giving 5 volt at the output. You can see the voltage on the meter.